Today, November 19th, 2025, at 3 p.m. Eastern Standard Time, NASA will finally release the images they have kept behind closed doors for more than a month. Images captured by the Mars Reconnaissance Orbiter on October 3rd during humanity's closest approach to an interstellar object. The target, 3I Atlas, a visitor older than our Sun, drifting into our solar system from the deep galactic dark. Normally, NASA publishes Mars imagery within hours, but this time, nothing. No raw frames, no preliminary previews, not even a hint of what the orbiter saw. And in that unusual silence, the world moved on without them. China released their own images first. Amateur astronomers detected strange activity around the object. And several scientists, including some of the most respected voices in astrophysics, began offering predictions that ranged from cautious to astonishing. Suddenly, this was no longer routine science. It became a global mystery, unfolding in real time. This story is not about conspiracy. It is about timing, about the unusual choreography between world powers, and about what happens when an object from another star system refuses to follow the rules. Because while NASA held their data, 3I Atlas kept changing. It produced jets pointing directly toward the Sun, something comets almost never do. Its colors shifted in ways that do not match typical comet chemistry. Its brightness flickered as if something inside the nucleus was responding to forces we do not yet understand. Today's reveal has grown far beyond a standard press briefing. Entire research teams are watching. Ground observatories are synchronized. Social media has turned this event into a countdown. And if you want to stay ahead of this unfolding mystery, if you want clear explanations without hype or panic, make sure you are subscribed. This story is accelerating, and you do not want to miss what comes next. Now back to the moment at hand. Somewhere deep within NASA's data pipelines, the highest resolution images ever taken of an interstellar visitor are about to be shown to the world. What will they reveal? A preserved core shaped by billions of years in interstellar space? Fragments from its near-Sun passage? A structure that explains its impossible jet patterns? Or something entirely unexpected, something that challenges what we think we know about objects born around other stars? 3I Atlas has defied expectations since the moment it arrived. It survived its near-Sun encounter when many predicted it would break apart. It displays a chemical makeup that appears to belong to a different kind of planetary system. And through all of that, the clearest images ever taken of such an object have remained unseen until today. So the real question isn't just, what will NASA show? It's, why did so many unusual things happen during the wait? Why did China move first? Why were amateurs the first to be? Spot the anomalies? And what does this object represent that slowed down a system built for rapid data release? Today's reveal marks the beginning of answers, and possibly the start of even bigger questions. Because if the new images confirm the strange behaviors we have been observing for months, then this moment won't be the conclusion. It will be the opening chapter of something far larger. The wait is over. The images arrive today, and whatever they show, they will change how we understand this interstellar visitor racing through our solar system. In modern space science, 40 days is an eternity. When the Mars Reconnaissance Orbiter captures images of the Martian surface, they typically appear in public databases within a day or two, sometimes within hours. The high-res camera, humanity's sharpest eye beyond Earth, runs on a rhythm that scientists trust. Students, researchers, and observatories around the world check its feeds daily. The entire system works because it is fast, transparent, and predictable. But the images of 3I Atlas, taken on October 3rd, when the object passed roughly 18.5 million miles from Mars, did not follow that rhythm. October 3rd came and went. No images. October faded into November. Still nothing. The raw data did not appear in the usual repositories. There were no preview frames, no calibration notes, no explanations. Every other MRO observation continued to flow normally except this one, and into that silence, speculation poured. Was there a transmission glitch? Possible, but rare for a spacecraft with such a long record of reliability. Calibration issues? Perhaps, but those are typically resolved quickly. A queue backlog? Maybe, though an interstellar object should outrank almost anything else on the schedule? Or was the delay connected not to a technical problem, but to the content of the images? The absence of information became information on its own. Scientists quietly discussed the delay in professional forums. Journalists slipped questions into unrelated press briefings. And the astronomical community, accustomed to NASA's open data philosophy, found itself waiting for imagery that everyone knew had already been captured, transmitted, and processed, but not released. What makes this delay historically unusual is not just the length, it is the context. 3I Atlas was already displaying behaviors that challenged established models. Its chemistry was unlike typical comets. Its orbital alignments appeared statistically odd. Its behavior near the Sun contradicted predictions about fragmentation and outgassing. And afterward, enormous jets stretching millions of kilometers and pointing in directions that defied standard comet physics sparked intense debate. Into this landscape, the Mars images represented something vital, a close-range, high-resolution truth check, not distant telescope views, not Earth-based interpretations distorted by atmosphere, but direct imaging from a stable platform with a proven track record. These images were supposed to provide clarity, not deepen uncertainty. Yet a delay of more than a month suggests something more involved. It suggests review, debate, deliberation. NASA is known for careful data handling, especially for complex imagery. Processed images must be calibrated, corrected, and precisely annotated. That is normal. But 40 days is far beyond normal. And while NASA remained quiet, the rest of the world did not. China released images from Tianwen-1. Amateurs shared surprising activity seen from ground telescopes. Independent researchers published real-time analyses of Atlas's behavior. The narrative kept expanding, but without NASA's voice, which is rare for an agency that usually frames major astronomical moments through coordinated releases and expert commentary. What we know is straightforward. The images exist. The Mars Reconnaissance Orbiter was in position. The HiRISE instrument functioned normally. The data reached Earth. And today, after more than a month of silence, NASA will finally show them in what they are calling a major announcement. What we do not know is why the release took this long, what those images contain that required such extended review, and whether the delay itself hints at something more complicated than routine processing. The mystery is not whether we will see the images, because today we will. The mystery is why they took 40 days, and what that timing suggests about the nature of what MRO saw when it turned its camera toward an interstellar visitor that, by all expectations, should not exist in our cosmic neighborhood but does. To understand whether more than a month of silence is truly unusual, we need context. NASA has faced moments before when unexpected data, surprising discoveries, or confusing observations forced the agency to move carefully. And when you study those moments, a pattern begins to emerge, subtle but revealing. When the first interstellar visitor, Oumuamua, flashed through the solar system in 2017, NASA did not release everything immediately. The discovery came from pan-stars in Hawaii, but confirmation required a coordinated global effort. Initial snapshots appeared quickly, but the deeper results, its strange reflectivity, its cigar-like proportions, the Spitzer data that redefined its size, took weeks to verify. But the delay made sense. The object was leaving fast. Different teams had different instruments. Scientists needed to be sure they were not misreading the data of something truly unprecedented. With the second interstellar visitor, 2I Borisov in 2019, things moved faster. Protocols had improved. Observatories were prepared. Images and spectra were released almost in real time. But even then, certain high-resolution Hubble frames came out in stages, timed with peer-reviewed papers and press briefings. This is standard astronomy procedure. Major discoveries receive major curation. The same thing happened with the methane story on Mars in 2020. Curiosity detected spikes that could have hinted at biological activity. NASA did not rush. They verified, re-verified, consulted outside experts, and only then made a cautious, carefully worded announcement. NASA learned long ago, especially after the 1996 Mars meteorite controversy, that extraordinary claims require extraordinary discipline. But the Mars Reconnaissance Orbiter images of 3I Atlas do not fit neatly into any of these patterns. This is not a case where the object is disappearing over the horizon. Atlas will remain observable into early 2026. This is not a biosignature that needs months of chemical verification. It is a photograph. And this is not a brand new type of instrument requiring new calibration techniques. HiRISE has captured and processed thousands of comet and asteroid images. So, what makes these images different? One possibility is entirely mundane. Maybe the nucleus looks slightly fragmented, or perhaps unexpectedly intact. Interesting, but not worth a 40-day delay. But if the images reveal structural features that do not match any known natural comet formation asymmetries, repeating surface patterns, geometric shapes, or something that challenges current models of how interstellar objects form, then the longer review period begins to make sense. NASA does not suppress data, but NASA does shape presentation. When Cassini discovered water jets on Enceladus, the announcement was choreographed. When New Horizons unveiled Pluto's heart-shaped ice plains, the release was paced deliberately, building a narrative. This is not deception, it is science communication, it is framing. Which brings us back to today. The key question is not whether NASA will release the images they will in a live global broadcast. The real question is how they will present those images, what they will emphasize, what they will call interesting, what they will call unexpected, and what they will quietly move past. And most importantly, why did it take more than 40 days to prepare a photograph? Even the James Webb Space Telescope, known for long calibration pipelines and proprietary access periods, publishes its timelines in advance. Everyone knows when to expect Webb data. The MRO situation is different precisely because it breaks the pattern. There was no warning, no technical advisory, just silence, followed by a sudden, high-profile announcement scheduled more than a month after the images were taken. History tells us NASA is not hiding evidence. History also tells us NASA is extremely careful about narrative control when something challenges established understanding. So, if these MRO images contain features that do not align with our current models of interstellar objects, then more than 40 days of internal review, expert consultation, and preparation for the inevitable questions is not suspicious. It is logical. And today, we will finally see whether that caution was warranted. The Mars Reconnaissance Orbiter has been circling Mars since 2006, quietly building the most detailed photographic archive of another world in human history. More than 66,000 images have flowed through its HiRISE camera, each one following a familiar, almost ritualistic path from the spacecraft to the public. And that rhythm is precise. HiRISE takes an image during one of the orbiter's regular passes. The raw data is stored, then transmitted to Earth during the next communication window, usually twice each day. It arrives through the Deep Space Network stations in California, Spain, or Australia. From there, it travels to the Operations Center at the Jet Propulsion Laboratory, where engineers apply geometric correction, radiometric calibration, and basic cleaning. This entire process usually takes less than 2 days. Then the images appear online on the HiRISE website, in the Planetary Data System, and across dozens of research platforms. The system is open, predictable, and transparent. Scientists rely on that cadence. The public relies on it, and for nearly 2 decades, it has rarely changed. Some images do take longer. Stereo pairs, complex terrain, experiments that require cross-mission coordination, all of these can extend processing time by several days, and when they do, the HiRISE team says so. Their operations log is famously honest, but the observation of 3I Atlas on October 3rd was logged as successful. The orbiter acquired the target. The data was sent. Nothing in the log hinted at a complication. Yet more than 40 days passed without a single pixel being released. The contrast becomes sharper when you compare it to everything else MRO captured in that same period. Craters, gullies, dust storms, polar frost, all appeared as expected. The stream never slowed, never faltered. Only the Atlas images remained absent. That specificity matters. It means the issue was not with the spacecraft, not with the camera, not with the transmission. It was with the data itself, or more precisely with what the data revealed. NASA has procedures for unexpected observations. When Curiosity sees something strange on Mars, an oddly shaped rock, an unusual mineral, a flash of light, the image is reviewed internally, but it still enters the public database quickly. Interpretation happens in parallel with public access. The Atlas case reverses that order entirely. Interpretation came first, silence followed. Only now, after private review lasting more than a month, is the public reveal being staged, and not quietly, not as a casual website update. Today, NASA is hosting a full live broadcast, multiple experts, scripted commentary, coordinated streaming across platforms, carefully prepared visuals. That level of production signals scientific weight. You do not mobilize NASA's public affairs machine for routine comet imagery. It also signals something else: framing. A press event lets NASA shape the story before anyone else sees the raw data. They can highlight certain features, downplay others, and set the interpretive tone for the global audience watching. This is not deception. It is responsible communication. When the science may challenge familiar assumptions, clarity matters. But it also means we are not getting a simple data dump. We are getting a presentation, a curated narrative built around selected images, which raises the central question: what are we about to see that requires this level of preparation? If the nucleus of 3I Atlas resembles every other comet we have imaged, irregular, battered, icy, there would be nothing here that requires 40 days of internal review. But if it looks different structurally, chemically, or morphologically different, then the extended silence makes sense. Today, we find out which truth we are living in. Today, the images captured in early October finally reach the world. Today, we learn whether the long pause was about routine caution or about something truly unusual. And if you want to follow each piece of this unfolding mystery as it happens, make sure you stay with us. What comes next could reshape far more than a single comet story. While NASA stayed completely silent through October, another space agency made a very different move. On November 7th, the China National Space Administration quietly released its own images of 3I Atlas. These images came from the Tianwen-1 Mars orbiter, captured on the exact same day NASA acquired theirs, October 3rd, during the comet's closest pass by Mars. But unlike NASA, China did not schedule an event. No countdown, no live stream, no 40-day pause. They simply uploaded the images to their official channels and let the world see them. It was a small gesture with enormous weight. This marked the first time in history that a Chinese spacecraft had ever photographed an interstellar visitor. It showcased China's growing ability not just to explore space, but to contribute scientifically on a global stage. And it sent a message: quiet, strategic, unmistakable. China stepped in to fill the silence NASA left behind. They knew the scientific community was waiting for Mars reconnaissance orbiter data. They knew the world expected NASA to set the pace. And by releasing their images first, China placed themselves at the center of the story. This is not the space race of the 20th century. This is something more subtle. Scientific soft power transparency used as influence. Timing used as leverage. Tianwen-1 was never designed to study comets. It is a Mars mission, China's first successful deep space program. But when 3I Atlas swept past, their team pivoted instantly. They recalculated pointing angles, retasked cameras, and performed what NASA calls a target of opportunity maneuver. That alone proves operational strength. Imaging a fast-moving comet with cameras intended for Martian landscapes is not simple, but Chinese engineers executed it flawlessly. The images themselves were modest, medium-resolution snapshots showing a glowing coma and faint jet structures. They lacked the razor-sharp detail high-rise is capable of. The nucleus appeared only as a few bright pixels. Surface features were impossible to see, but China released what they had. No hesitation. And almost immediately, researchers around the world dug in. Photometric measurements, brightness modeling, comparisons with ground-based telescopes. For several weeks, China did not simply contribute to the science, they led it, because for several weeks, their images were the only images. That contrast matters. It shaped the narrative, It set expectations, and it raised a quiet but unavoidable question. If China could release their images within a month, why was NASA taking more than 40 days? Maybe it was technical, maybe it was organizational, or maybe the high-rise data showed something worth extra review. We do not know. But we will today, because today, NASA's higher resolution images finally emerge. And once they do, researchers will begin lining China's images up beside NASA's frame by frame. We will see whether Tianwen-1 missed anything significant, whether NASA's delay added clarity or complexity. Regardless, November 7th marked a turning point. China did not just observe an interstellar object, they shaped humanity's first impression of it during a critical moment. They contributed real data, on a real timeline, while others hesitated, and in doing so, they revealed something important about this new era of space exploration. The first country to release data shapes the questions everyone else will ask. As we move deeper into the mystery of Three-Eye Atlas, that dynamic is not a footnote, it is part of the story. And if you want us to keep uncovering how this global puzzle fits together, make sure you stay with us. What comes next is where the story really begins to accelerate. The images released by China on November 7th were not spectacular. They were not the kind of high-definition, poster-worthy frames agencies love to showcase. But they were revealing sometimes in what they showed, and sometimes in what they could not. In the Tianwen-1 photographs, Three-Eye Atlas appeared as a bright, condensed point, the nucleus surrounded by a softly glowing halo of dust and gas. The nucleus itself covered only 2 or 3 pixels, far too small for any structural detail. No cliffs, no jets carving out shadows, no surface geometry. But even with such limited resolution, there was movement, there was direction, there was behavior. The coma was not symmetrical. Instead of a smooth circle, it stretched unevenly, as though something beneath the surface was pushing harder on one side than the other. This is the unmistakable signature of outgassing material erupting in consistent directions as sunlight hits pockets of volatile ice. And then came the strange part. On what should have been the sunward side, there was a faint, persistent extension, not a tail flowing away from the sun, but a structure appearing to point toward it. Ground-based astronomers had been arguing about this feature for weeks, some calling it a processing artifact, others dismissing it as an optical illusion. But now China had seen it too, from a different angle entirely. When 2 separate vantage points detect the same anomaly, the debate shifts. What was easy to shrug off suddenly demands attention. Another detail stood out: the coma's color profile, or the lack of one. Typical comets show subtle gradients because different molecules emit different wavelengths. Water gives a bluish cast. Carbon compounds can shift things toward green or red. But the Tianwen-1 images displayed almost no color variation at all, a uniform glow, a single chemical story. This matched what the James Webb Telescope had been whispering months earlier. The comet is overwhelmingly dominated by carbon dioxide, far more than water, a composition that behaves differently, a composition that responds violently to even mild sunlight, and perhaps a composition that creates the strange jet patterns observers have been struggling to explain. Yet the Chinese images also showed something reassuring. The nucleus appeared intact. Many models predicted fragmentation as the comet rounded the sun. Some expected it to break apart entirely. But the Tianwen-1 images showed a single, concentrated point. No debris field, no separated fragments. This hinted at structural resilience, either a stronger internal architecture or a protective crust, hardened by eons drifting through the cold between stars. Not unusual enough to be sensational, but unusual enough to make scientists pause. The tails revealed even more. The classic dust tail faint, the gas emissions strong. Another clue pointing back to carbon dioxide volatility rather than water-driven activity. And that sunward extension? Still there, still unexplained. Chinese scientists suggested natural explanations, perspective effects, rare dust, grain properties, complex rotation dynamics, all possible, all physically plausible, but none of them entirely satisfying. The images did not reveal a smoking gun, but they did reveal a puzzle, and puzzles become harder to ignore when two independent spacecraft capture the same strange behavior. What the Chinese images truly accomplished was not solving the mystery, but sharpening it. They made the silence from NASA feel longer. They made the 40-day wait for high-resolution data feel heavier. And they made today's upcoming reveal feel far more urgent. China delivered the appetizer, just enough to spark curiosity, but nowhere near enough to answer the growing questions. What NASA is about to release today is the main course, the first sharp, detailed look at an interstellar nucleus ever captured from close range. And if you want us to break down those images the moment they arrive, make sure you stay with us. This story is just beginning to unfold. As the world waited for official images, a very different group stepped into the spotlight: amateur astronomers. Not casual stargazers, but highly skilled observers armed with equipment that rivals small professional observatories. Many of them operate remote telescopes under dark skies, equipped with advanced CCD cameras, guided mounts, spectrographs, and software that lets them measure brightness with surgical precision. And unlike space agencies, they do not wait for approval. They see something unusual, they point their telescopes, and they publish within hours. Throughout October and early November, while NASA stayed silent, this global network tracked 3i Atlas night after night, building what became the first real-time record of the comet's strange post-perihelion behavior. It started with simple imaging time series photographs from New Mexico, Australia, Japan, Europe, stitched across time zones to create almost continuous coverage. But these observers soon began noticing patterns. The sun would jet, the feature some professionals doubted kept showing up. Different nights, different observers, different equipment, and always pointing in the same direction relative to the sun. That consistency mattered. Other amateurs shifted to photometry, measuring subtle color and brightness changes. They detected regions that were slightly redder, others slightly bluer, evidence that the coma was not chemically uniform. A few even captured low-resolution spectra that confirmed what the James Webb Telescope had hinted at. The comet was dominated by carbon dioxide, far more than water. Then came the surprising part: brief, mysterious spectral spikes, lines that did not match known comet molecules, lines that appeared and faded within hours. It wasn't proof of anything exotic, but it was a sign that Atlas was more dynamic, more unpredictable than standard comet models allow. By early November, amateurs had effectively built a parallel scientific record, updating the world every day with new images, new measurements, and new theories. Professional astronomers took notice. Graduate students started incorporating amateur light curves into their research. Conference slides began citing backyard spectrographs. The line between amateur and professional blurred almost completely. One of the most significant findings came from observers specializing in photometric monitoring. They documented erratic brightness spikes, sharp increases, and sudden fades that did not align with rotation models. Some suggested these were outgassing eruptions, internal pressure breaking through a hardened crust and releasing volatile pockets in violent bursts. It was speculative, yes, but grounded in physics. Meanwhile, nightly images revealed a complex jet network emerging after perihelion. Sunward jets, lateral jets, the faint antisolar tail, multiple outflow directions, all active at the same time. This level of complexity is rare. Solar system comets usually behave more predictably, but 3i Atlas was behaving like something else, and the amateurs kept catching it. The biggest strength of these observers was continuity. Professional telescopes operate on tight schedules, every hour booked, every target competing for time. But amateurs could watch Atlas as long as it was above the horizon. When a brightening spike appeared in Japan on November 2nd, European observers confirmed it within hours. By the time the comet rose over America, hundreds of eyes were already searching for the same feature. This rapid global relay created a dataset NASA could never produce alone, a continuous, evolving portrait of the comet's behavior captured in real time. But even the best amateur equipment has limits. They could not see the nucleus. They could not resolve individual vents. They could not image the fine-scale structures shaping those unusual jets. What they produced was context weeks of behavior leading up to today's reveal. But the decisive questions require spacecraft resolution. That's why everyone, amateurs and professionals alike, are now looking to NASA's imminent images. They're waiting to see whether the high-resolution frames finally confirm the patterns the amateurs have documented, or contradict them entirely. Either way, the amateur astronomers deserve credit. They didn't discover the comet. They didn't capture the sharpest images. But they did something no spacecraft can do. They watched 3i Atlas continuously during its most unpredictable phase, documenting every flare, every change, every anomaly. And today, their months of vigilance finally meet the moment of truth. If you want us to break down how the amateur data lines up with NASA's images the moment they drop, make sure you stay with us. What comes next could redefine this entire story. If you're still with us right now, you're officially part of the tiny group that actually follows these deep dive investigations all the way through. And if you want to help us keep pushing this research forward, you can tap like and subscribe. It genuinely helps. Now, let's dive in. In normal comet physics, everything flows away from the sun. Sunlight warms the nucleus. The ice turns into gas. Dust gets lifted off the surface, and the solar wind pushes all of it outward. Every force in the solar system agrees on that direction. It's one of the simplest rules in space science. But 3i Atlas didn't follow that rule. As far back as July, observers began seeing something that didn't belong in any comet model. A faint extension of the coma seemed to point toward the sun instead of away from it. At first, people dismissed it. One telescope angle can fool you. Atmospheric distortion can bend light. And a single weird frame is never enough to call something real. But then the reports kept coming. Different countries, different telescopes, different angles, and the feature kept showing up. After perihelion, when the comet came back into view, the unusual structure was no longer faint. It was sharp, stable, and clearly directed toward the sun. Not as a smudge, not as an illusion. It looked like an actual jet, and that was the moment everyone realized this wasn't a glitch. Here's the problem. Gas should not move toward heat. Outgassing is driven by sunlight. That's basic thermodynamics. Yet here was a jet streaming straight at the heat source. Scientists immediately tried to explain it within known physics. The first idea blamed rotation. If the comet were tumbling in a weird, chaotic way, maybe pockets that heated earlier could still be releasing gas in directions that no longer matched the current angle of sunlight. But the numbers didn't work. The jet didn't drift. It didn't wobble. It held the same direction night after night. A rotating nucleus should have made it sweep around like a lighthouse beam, but it didn't. So researchers looked at composition. 3i Atlas is dominated by CO2 ice, which behaves very differently from water ice. CO2 can sublimate explosively, even at lower temperatures. Maybe cracks in the crust were launching gas in unusual directions. It sounded promising, but even that couldn't explain how steady and clean the sunward jet was. Random eruptions don't produce a perfectly aligned stream. Then came the electromagnetic explanation. Comets release charged particles. Charged particles interact with the solar wind's magnetic field. Under rare conditions, that interaction can push material in strange directions, even sunward. This was technically possible, but it required an extremely precise set of conditions. A cosmic coincidence. And then there was the theory researchers whispered about but didn't want to say publicly. Maybe the jet wasn't reacting to sunlight at all. Maybe it was reacting to something happening inside the comet. Internal pressure, exotic ices, subsurface layers releasing gas along paths shaped by internal structure rather than solar heating. Ordinary comets don't have internal heat sources. But this isn't an ordinary comet. It didn't form in our solar system. It formed around a different star, under different conditions, in a different environment. It might store energy differently. It might fracture differently. It might vent differently. By November, nobody doubted the sunward jet existed. The debate was about what could possibly cause it. And that brings us to NASA's images releasing today. Everything we've seen, the amateur images, China's early data, the ground-based observations tells us the jet is real. But none of that shows where it comes from on the surface. A crack? A depression? A ridge? A pattern? Those details matter. They tell us whether the jet is random, structural, or something much stranger. The comet is pointing a jet toward the sun. It shouldn't be possible, but it's happening anyway. And today, for the first time, we finally get to see what's causing it. Astronomers often talk about something called an anti-tail, and normally, it's nothing unusual. When a comet leaves behind a long trail of dust along its orbit, and Earth happens to line up with that trail from just the right angle, the dust can look like it's stretching toward the Sunday. It isn't. It only appears that way because of perspective. The dust is still traveling in the normal direction, away from the sun, pushed by sunlight and the solar wind. But the anti-tail on the interstellar comet known as 3I Atlas doesn't follow that rule. It behaves like a real, physical structure, even though by every standard model of comet behavior, it shouldn't exist at all. For one thing, it refuses to disappear when Earth's viewing angle changes. A normal perspective-based anti-tail only shows up when alignment is perfect. But observers kept seeing this structure no matter where Earth moved in its orbit. And it wasn't just Earth. When the orbiter around Mars captured its own images from a completely different angle, the same structure appeared there too. A perspective illusion simply cannot survive changes like that. Even stranger, this structure changes over time. It brightens, fades, develops knots and clumps, and shows shifting internal texture. Perspective effects do not evolve. They do not come alive. They stay static. But this structure behaves like something that is actually out there in space. That leaves only one conclusion. The anti-tail of 3I Atlas is not an illusion. It is real material moving in a direction that standard comet physics can't easily explain. One possibility is that the anti-tail is made of unusually large dust particles. Small particles get pushed away from the sun by light. Larger particles, especially if they are millimeter or centimeter sized, barely feel that push at all. Their motion is controlled by the direction they were launched from the comet's surface. If vents on the day side of the comet released these heavier particles with the right velocity, some of them could travel on paths that appear to point back toward the Sunday. If that were the case, you'd expect the structure to be broad and diffuse. Instead, the anti-tail of 3I Atlas is narrow, tightly focused, almost like a beam. That kind of precision usually requires fast rotation to funnel material through specific pathways, but the rotation period of this comet, around 16 hours, is far too slow to create such a sharply defined structure. So researchers looked to another idea: electromagnetic forces. Dust can become electrically charged when exposed to ultraviolet, sunlight, or through collisions with charged particles in the coma. If that charge is strong enough, and if the magnetic field carried by the solar wind interacts with it in just the right way, it might guide the dust into unusual shapes. It's possible, but it requires a very specific balance of conditions that we don't normally see in comets. The most surprising explanation is the simplest. This comet may be made of material we have very little experience with. If the dust has unusual reflectivity or unusual mass, or if its composition is dramatically different from the comets formed in our own solar system, it might behave in ways our existing models don't fully predict. Whatever the cause, the anti-tail is not behaving like anything familiar. It is stable, it is structured, and it seems to be tied to physical processes happening on or near the comet's surface. And that is why today's high-resolution images matter so much. From Mars's perspective back on October 3rd, the spacecraft saw the comet from a completely different side. If the anti-tail appears there too, and all signs suggest it will, its shape and thickness might reveal whether it's made of massive particles, charged material, or something even stranger. The anti-tail is one of the clearest signs that 3I Atlas isn't just another comet passing through our solar system. It behaves like something shaped by forces we don't fully understand. And today, for the first time, we might get a closer look at the structure that has challenged comet science since the moment it first appeared. When most comets glow green, we know exactly why. Ultraviolet light from the sun breaks apart carbon-based molecules in the coma, especially a molecule called diatomic carbon, which scientists usually write as C2. When C2 gets excited by sunlight and then relaxes, it emits a bright green light around 516 nanometers. That's why so many comets look green. It's predictable. It's standard. It's one of the most well-understood parts of comet chemistry. So when observers began reporting that 3I Atlas was glowing green, nobody thought twice. The assumption was simple. There must be plenty of C2 in the coma. Except when astronomers pointed spectrographs at the comet, the expected C2 signal wasn't there. The green colour was strong, but the C2 lines that should have caused it were far too weak. In some observations, they were almost missing entirely. That mismatch created a problem. If the comet truly contains only small amounts of C2, then where is all that green light coming from? At first, scientists wondered if something was off with the images. Maybe camera sensors exaggerated the green channel, or maybe atmospheric effects distorted the colour. But multiple observers using different equipment across different continents reported the same green glow. Even photometric measurements, actual numerical brightness, readings confirmed that the green emission was real. So the puzzle deepened. Researchers began checking other possible sources of green light. Oxygen can emit green at 557 nanometers, but the oxygen signal in 3I Atlas was far too weak. Iron compounds can glow green, but none were detected at levels that could explain the brightness. Complex organic molecules can fluoresce green, but again, no evidence of them appeared clearly in the spectrum. And then came the strangest part. The green glow wasn't steady. It pulsed, it brightened, and faded over hours. That means something active is happening, some material is being released in bursts, not continuously. One idea is that the comet's surface has been altered by billions of years of cosmic radiation in interstellar space. This could create exotic chemicals that don't exist on typical solar system comets. When ultraviolet sunlight hits those chemicals, they could fluoresce in ways we haven't catalogued yet. Another possibility involves plasma. The coma of 3I Atlas is partly ionized. If electrons are being accelerated by the sun's magnetic field, they could slam into molecules and excite them, producing green light through a completely different mechanism than normal solar fluorescence. That would also explain the rapid flickering of brightness. Nothing here breaks physics, but it does stretch our models, because everything we know about cometary emission spectra comes from comets born in our own solar system. 3I Atlas didn't form here. It comes from a star system with a completely different chemical history. Today's images won't solve this puzzle by themselves, they're photographs. Not spectra, but they might show surface patches or fresh exposures where unusual material is being released. And if NASA pairs those images with new spectroscopic data, we may finally learn what's producing that bright green glow, or discover that this interstellar visitor has one more surprise that we're not yet equipped to explain. Comets usually glow green for one main chemical reason. When ultraviolet light from the sun breaks apart carbon-bearing molecules in a comet's coma, especially the molecule known as C2, the fragments enter excited states and release energy as green light. It is one of the most predictable signals in comet science. If a comet looks green, it almost always means the gas around it is rich in C2. That is why observers were surprised when the comet called 3I Atlas began showing a clear green glow, even though early spectroscopic data showed almost no C2 at all. The colour was real. Multiple teams measured the intensity at the exact wavelength where C2 normally shines, but the molecule itself was barely present. The glow didn't match the chemistry. Some researchers wondered if something about the cameras or the processing made the comet look greener than it really was. But even precise, calibrated measurements confirmed the same thing, an unusually strong green emission coming from something other than C2. The next assumption was oxygen, which can also emit green light, but the oxygen signatures were far too weak to explain what observers were seeing. Other possible molecules didn't match either, so scientists started looking deeper. One idea focuses on the surface of 3I Atlas itself. If the comet spent billions of years drifting through cosmic radiation between star systems, its outer layers may contain unusual compounds we rarely or never see in comets from our own solar system. When ultraviolet light strikes those compounds, they could fluoresce in ways we are not familiar with, producing the green glow without the usual C2 signature. Laboratory experiments are already underway to test whether ice mixtures exposed to deep space radiation can mimic what we're seeing here. Another possibility involves plasma effects. The coma around the comet is partially ionized, and electrons moving through electric fields inside that plasma could excite molecules in unusual ways. This could create green light through collisions rather than through standard photon absorption. It's a more exotic explanation, but the ion and dust environment around 3I Atlas is strange enough that scientists aren't ruling it out. What makes the puzzle even deeper is that the green glow isn't stable. It fades, intensifies, and sometimes nearly disappears in a matter of hours. That suggests bursts of activity or the release of different materials at different times. It is not a simple chemical process. It is dynamic, just like the jets in the antitail, which already showed us this comet does not behave like anything we have studied up close before. The rotation of the comet adds to the mystery. Early observations suggested a rotation period of around 16 hours, which is normal. But as more data came in, the pattern became murky. The brightness variations did not repeat cleanly. Sometimes the comet appeared to tumble. Sometimes it spiked in brightness for just minutes at a time, then calmed down. These spikes happened too often and too strongly to be explained by typical comet outbursts alone. Scientists began to suspect the nucleus might be irregular, or even composed of multiple loosely connected pieces. A rubble pile structure could rotate in complicated ways, especially if powerful jets are pushing on different parts of it unevenly. But if it were that fragile, many expected it to break apart when it passed closest to the Sunday. It didn't. Another theory suggests that strong outgassing from specific regions might be causing the rotation axis to wobble, a motion called precession. That would explain why the brightness changes don't line up perfectly with simple rotation. But without clear images of the nucleus, all of this remains guesswork. And that is where NASA's images finally come into the picture. The single high-resolution frame cannot show rotation directly, but it can reveal the shape of the nucleus. If the comet is elongated, tumbling becomes more likely. If it has sharply contrasting surface zones, the uneven brightness starts to make sense. If it appears fractured or made of multiple connected components, then the rubble pile model becomes the strongest explanation. The chaotic rotation of 3I Atlas remains one of its most compelling mysteries. It might be telling us that the comet is structurally strange, chemically unusual, or undergoing processes we haven't seen in interstellar objects before. Whatever the truth is, it is encoded in the shape of the nucleus details hidden inside the NASA images we are finally about to see. Most comets form a smooth, glowing cloud of gas and dust around their core. It's called the coma, and under normal conditions it fades outward in a gentle gradient, brightest near the center, softer toward the edges. It behaves exactly the way the physics textbooks say it should. But 3I Atlas refused to behave. Starting in late August, astronomers began noticing something strange in deep images. The coma wasn't smooth. Instead, it looked layered, almost like ripples frozen in space, concentric arcs, rings, shells of brightness stacked around the nucleus. And these were not faint illusions. They were structured, defined, persistent. By early October, some observers counted 4, sometimes even 5 distinct shells at different distances from the nucleus. Now, comet scientists have seen shell patterns before, but never like this. Normally, shells appear briefly after a sudden outburst when trapped gas bursts from beneath the surface and sends a pulse of material outward. That pulse expands, slows, and fades. The shell disappears. It's a momentary event. But the shells around 3I Atlas didn't fade. They stuck around. They held their shape for weeks, even as new shells formed closer in. It was like watching an ancient tree grow rings one after another, except in open space. For these shells to last that long, they couldn't be made of just gas. Gas diffuses quickly. To stay visible for weeks, the shells had to contain dust, actual solid particles carried outward in bursts. But here's the problem. 3I Atlas is dominated by CO2 ice, and CO2 sublimates cleanly. It usually produces less dust, not more. So where was all this dust coming from? One theory gained traction. The surface crust of 3I Atlas, hardened by billions of years in interstellar radiation, might be cracking like old pottery. Every time internal pressure builds beneath that crust, it fractures. And when it fractures, it doesn't just release gas, it spits out pieces of the crust itself. Dust, grains, fragments, enough to form persistent shells. This would also explain the regular spacing. The shells seem to form roughly every 12 to 16 hours, almost matching the comet's rotation. Every time a fractured region turned into sunlight, it warmed, pressure built, and pop, a new shell. But again, the persistence was the real mystery. These shells extended hundreds of thousands of kilometers outward, each one a snapshot of an earlier eruption. Inner shells merged, outer shells drifted, some brightened, some dimmed. It was dynamic, layered, and unlike anything normally seen in comets. Other scientists propose more exotic ideas like photochemical reactions forming brightness rings at specific distances, or charged dust interacting with the solar wind's magnetic fields. That could, in theory, organize particles along invisible lines of force, but that would require unusually strong plasma activity for a comet, something we've never measured before. By mid-November, the coma of 3I Atlas looked less like a cloud and more like a cosmic fingerprint, each ring marking a moment when the comet's crust ruptured and vented its ancient interior into space. We won't see these shells in the Mars Reconnaissance Orbiter images today. They're far too large scale for a spacecraft camera focused tightly on the nucleus. But what we will see could reveal the source of those eruptions. Cracks, rifts, freshly exposed terrain, areas where the crust looks different from everything around it. Because if the surface tells the same story the coma does, then 3I Atlas isn't just outgassing, it's evolving, breaking, shedding layers of material that haven't seen sunlight since before our sun even existed. And those shells spreading outward like ancient breaths frozen in motion are the evidence. They're the trail of an object shaped in another star system, now telling its story in ours. Among the many voices weighing in on the mysteries of 3I Atlas, few have attracted as much attention or stirred as much controversy as Harvard astrophysicist Avi Loeb. He's one of the most famous and most polarizing scientists working today. And whether you love his ideas or think they push too far, one thing is certain: he has a talent for walking straight into the questions everyone else is afraid to touch. Loeb first gained worldwide attention back in 2017 when the first interstellar visitor, Oumuamua, swept past Earth. Its strange acceleration and unusual shape led him to suggest a possibility most astronomers wouldn't dare put in print, that it might have been technological. Not proof, not a conclusion, a possibility, a question worth asking, and that same pattern is repeating now with 3I Atlas. Loeb argues that this object shows a cluster of anomalies, 12 in total, that are difficult to explain all at once with standard comet physics. We've already talked about some of them: the sunward-facing jets, the anti-tail, the strange green glow, the multi-shell coma, but Loeb includes even more in his list: the unusual alignment of its incoming trajectory with the plane of the solar system, the strength of its survival at perihelion, the timing of its arrival, and the sheer size of the object compared to other interstellar visitors. His argument is simple: any one anomaly on its own might be natural, but when an object shows a dozen things that sit at the far edges of what comets normally do, you at least consider alternative explanations. His newest study, released in early November, focuses on those massive post-perihelion jets stretching millions of kilometers behind the object. According to his calculations, the amount of material needed to sustain jets that large would normally strip 10 to 20% of the comet's total mass within a few weeks. And yet, 3I Atlas looks intact. No catastrophic breakup, no runaway disintegration, no obvious signs of losing that much mass. So Loeb asks the question others avoid: if solar heating can't explain the jets, then what can? Could there be internal processes, chemical, energetic, or something beyond our current models that drive them? And yes, he includes the possibility, however small, of technological mechanisms. The scientific reaction to this has been split. Some researchers appreciate the boldness. Science needs people who are willing to challenge deeply held assumptions. Even when those ideas end up wrong, they force the community to sharpen its reasoning. Others worry that jumping to exotic explanations breaks the discipline's core values, that you should always exhaust natural possibilities before reaching for extraordinary ones. One of Loeb's most outspoken critics is Jason Wright from Penn State University. Wright specializes in the search for technosignatures, meaning he's not dismissing unusual possibilities out of principle, but he argues that most of the so-called anomalies aren't anomalies at all once you account for uncertainty, small sample size, and the fact that we've only seen 3 interstellar objects ever. Some will arrive on odd trajectories, some won't break apart when expected, some will behave strangely simply because they were formed around different stars under different conditions. Other researchers fall somewhere in the middle. They agree 3I Atlas is strange. They agree its behavior pushes the edges of what comet models predict, but they argue that strange doesn't automatically imply artificial. Interstellar comets come from environments that may not resemble our solar system at all. They might contain chemical structures, radiation-processed ice mixtures, or internal architectures that we've simply never encountered before. Darrell Seligman points out that with only 3 detections, we don't know what normal even means for interstellar objects. Maybe 3I Atlas isn't unusual. Maybe this is how most interstellar comets behave, and our solar system comets are the odd ones out. Others, like Jacqueline McCleary, emphasize that the anomalies might reveal where the object was formed. Its carbon dioxide heavy composition points to a birth far beyond the carbon dioxide ice line of its original star system, possibly in a region colder and darker than anything inside our solar system. Studying 3I Atlas isn't just about solving mysteries, it's about sampling material billions of years old from a star that may not exist anymore. What's happening now is bigger than a debate about one object. It's a debate about how science should handle the unknown. Do you stay conservative until every natural explanation is ruled out? Or do you remain open to low probability ideas when the data genuinely strain conventional models? Most astronomers sit somewhere between these 2 extreme views. They remain skeptical, but not dismissive, curious, but cautious, waiting for better data. And that is exactly what today brings. Because if the incoming MRO images show a nucleus shaped like a natural comet with chaotic terrain, fractured cliffs, and irregular geometry, then the conservative camp gains strength. But if the images reveal patterns, structures, or symmetries that look engineered, then suddenly Loeb's cautionary questions won't seem fringe anymore. And there's always the third possibility, something genuinely new, something nobody predicted, a surface texture that doesn't match comets, a composition that defies chemistry, a morphology that forces every model back to square one. Whatever the images reveal, they will change the conversation. They might deepen the mystery, they might clarify it, but they will absolutely not leave things where they are now. Because 3I Atlas has already done something extraordinary. It has forced us to reconsider what we think we know about interstellar visitors, how rare anomalies truly are, and how ready we are or aren't to recognize something genuinely different when it arrives at our doorstep for the first time in human history. If we want to understand whether 3I Atlas is truly unusual, we first need to understand what scientists expect an interstellar object to look like in the first place. Everything begins in a young star system. When a new star forms from a collapsing cloud of gas and dust, a wide rotating disk forms around it. From that disk, planets, moons, asteroids, and comets take shape. But not everything stays neatly in orbit. As giant planets form, their gravity starts stirring the system like a cosmic blender. Some objects get nudged outward, some collide, and some are thrown with enough speed to escape entirely, launched into the galaxy as wandering debris. Every star system does this. Over billions of years, the Milky Way becomes filled with trillions of these exiled bodies, raw fragments of ancient planets and primordial ice worlds, drifting between the stars. Most of the time, they travel unseen, but occasionally, one crosses paths with our solar system. We have only detected 3 of them so far: Oumuamua, 2I Borisov, and now 3I Atlas. And the truth is, with such a tiny sample, we barely know what normal is supposed to look like. Theoretical models predict enormous diversity. Interstellar objects should come from different kinds of stars: ancient metal-poor stars, young metal-rich stars, binary systems, even systems that no longer exist. Their chemistry could vary wildly. Some might be rich in graphite, some rich in silicates, some with exotic ices we rarely see here. And all of them, after drifting through interstellar space for billions of years, would develop a radiation-processed crust, a hardened outer layer reshaped by cosmic rays, hiding a pristine interior that still remembers its birthplace. Models also predict size differences. Smaller objects should be far more common, while truly large ones should be rare. Oumuamua matched the expectation, barely a few hundred meters. 2I Borisov was larger but still typical. 3I Atlas, however, may be far bigger. Some brightness measurements suggested a size of several kilometers, maybe even tens of kilometers. If that were true, finding such a large object as only our third detection would challenge the models. It would suggest the galaxy contains far more big interstellar objects than we thought. But there is a catch. Size estimates from brightness can be misleading. If 3I Atlas has a highly reflective surface, it could appear brighter and therefore larger than it really is. Hubble data later suggested an upper limit of only a few kilometers, maybe even less than 1 kilometer. So even here, uncertainty rules. Models also make predictions about motion. Most interstellar objects should travel at speeds between 20 and 50 kilometers per second relative to the Sun. 3I Atlas entered at about 58 fast, but still believable. Its direction, though, is what caught attention. It arrived almost perfectly aligned with the solar system's planetary plane. Statistically, that alignment has roughly 10% probability. Not impossible, just slightly unusual. Some researchers argue that coincidences like this are expected when you've only seen 3 objects. Others argue the timing and alignment are too convenient to ignore, and that disagreement highlights the deeper issue. With such limited data, theory can guide us, but it cannot fully constrain what we see. Interstellar objects could also carry chemical fingerprints from their birth environments. A star system rich in carbon might send out carbon-heavy bodies. A star system with extreme temperatures might produce objects coated in exotic ices, and after spending billions of years exposed to the cosmic background, these materials change. Water ice breaks apart. Organics fragment. Carbon dioxide becomes more dominant. 3I Atlas, with its oxygen-rich and carbon dioxide-heavy signature, might simply be showing us the natural result of interstellar aging, not an anomaly, but an example of chemistry shaped in a distant system under conditions unlike anything in our own. This is why the anomalies of 3I Atlas matter, not because they automatically imply something unnatural, but because our theoretical framework is still thin. Every time an interstellar object passes through our solar system, we have a tiny window to update our models, a chance to calibrate what normal really means. And today's images from the Mars Reconnaissance Orbiter will push this conversation even further. The surface features visible in those images, whether fractured crust, layered deposits, smooth planes, or irregular broken geometry, will give theorists real constraints instead of guesses. They will let scientists test whether the object's shape matches the expectations for a body hardened by cosmic radiation, whether its surface reflects billions of years of interstellar weathering, or whether it shows something entirely unexpected. The mystery of 3I. Atlas isn't just about what it is, it's about what it represents. A messenger from the galactic dark, a fragment of a planetary system that may have died before Earth even existed. Every detail we uncover helps refine the models. Every anomaly pushes us to update our assumptions. And every observation teaches us a little more about the unseen population of objects that drift silently between the stars. 3I Atlas carries the history of another sun. Today, we read a little more of that history. Our entire understanding of interstellar visitors comes from just 3 objects, 3 encounters, across 8 short years. And each one tells a completely different story about what drifts between the stars. The first was Oumuamua, discovered in late 2017. Before its arrival, interstellar objects were only a prediction on paper. Astronomers were certain they must exist, because planetary systems naturally eject debris during formation. But until Oumuamua, no one had ever seen one. Oumuamua didn't just appear. It arrived fast, silent, and deeply strange. It showed no visible comet tail, no obvious outgassing, nothing that made it look like a normal comet. Yet it accelerated. Something pushed it slightly, in a way gravity alone couldn't explain. Some scientists argued for faint, invisible outgassing, others suggested exotic chemistry, and a few, including Avi Loeb, asked whether its behaviour might hint at technology. But before anyone could answer, Oumuamua was already gone, fading into deep space long before telescopes could gather enough data. Then came our second visitor in 2019, 2I Borisov. If Oumuamua was mysterious, Borisov felt familiar. It behaved like a classic comet, bright coma, long tail, steady outgassing. It was a relief. It suggested most interstellar objects might simply be normal comets formed around other stars. But even Borisov carried surprises. Its unusually high carbon monoxide levels hinted at formation in an extremely cold region, colder than anything in our own system, and it appeared chemically pristine, as if it hadn't been drifting between the stars for very long. Two objects, two extremes, one strange, one familiar, and then the third arrival, 3I Atlas. It sits right between the first two, but at the same time far outside what we expected. Unlike Oumuamua, 3I Atlas is clearly active, releasing gas and dust. Unlike Borisov, its dominant volatile isn't water or carbon monoxide, it's carbon dioxide. And unlike either of them, 3I Atlas exhibits multiple physical behaviours that simply don't match the standard textbook description of how comets behave. Compared to Oumuamua, 3I Atlas is larger, slower, and far easier to observe over long periods. It doesn't hide its activity, it displays it boldly. But Oumuamua was smooth and silent, while 3I Atlas is chaotic jets shooting toward the sun, complex rotation, shells forming in the coma, and structural features that don't fit well with simple models of natural outgassing. Compared to Borisov, the difference is even more striking. Borisov behaved like a normal comet from a foreign star. 3I Atlas behaves like something ancient, something processed, something that's been exposed to billions of years of cosmic radiation, a thick crust, a carbon dioxide-rich composition, activity driven in unexpected directions, and behaviour that suggests a long, difficult life wandering between the stars. The three objects almost feel like three chapters in a story. Oumuamua could represent the most fragile type, small fragments or rocky bodies ejected relatively recently, still close in character to their birth systems. Borisov might represent fresh, icy bodies tossed out during early planet formation, carrying the chemical imprint of young stellar disks. 3I Atlas may be something older, something shaped not just by its birth environment but by billions of years, drifting through the galaxy. Its chemistry, its crust, and its anomalies may reflect conditions from the ancient universe, when stars were forming differently, when elemental ratios were different, when planetary systems produced materials that no longer exist in our era. If this interpretation is correct, then each interstellar visitor we've seen represents a different population from different times, different places, and different eras of the galaxy's history. But we don't know yet. 3 data points can't define a population, and the most unusual one, 3I Atlas, is still leaving us with more questions than answers. What we do know is that 3I Atlas breaks the pattern. It tells us the diversity of interstellar objects is far wider than we assumed. Some may be pristine, some may be heavily processed, some may behave like normal comets, and some may display behaviours that challenge our models entirely. Today's MRO images may show whether 3I Atlas is simply an extreme example of natural diversity, or something that forces us to rethink our assumptions entirely. No matter what they reveal, one thing has become clear. The universe sends us visitors in many forms, and 3I Atlas might be the most revealing one yet. Today, NASA steps onto the stage with the kind of build-up they reserve for moments that matter. They don't assemble multiple mission teams, prepare live commentary, synchronize releases across platforms, and block out media time just to show a slightly sharper picture of a comet. When NASA moves like this, it means they believe what they're about to show could reshape the conversation. And at the center of it all is 3I Atlas. The obvious expectation, the one everyone is bracing for, is direct, high-resolution imaging of the nucleus itself. Because on October 3rd, when 3I Atlas swept past Mars just 4 days after perihelion, NASA's Mars Reconnaissance Orbiter had a front row seat, and its high-rise camera, arguably the sharpest eye humanity has ever put into orbit, was pointed right at it. From Mars, 3i Atlas was still 18.6 million miles away. That's unimaginably far for surface imaging, yet HiRISE is powerful enough that under perfect conditions it could resolve meter-scale features even at that distance. No telescope on Earth can do that. No spacecraft anywhere else had that geometry. This was a once-in-a-lifetime alignment. So what might those images show? We might finally see the true shape of the nucleus. Is it spherical, elongated, split, bilobed like Comet 67P? Or something stranger, something no comet model predicts? Shape alone would answer half a dozen open questions. It would tell us whether the tumbling light curve makes sense. It would constrain density, structural strength, and how 3i Atlas survived the violent heat of perihelion. We might see surface texture smooth regions, rough regions, layered, terrains, fracture networks. If vents or cracks are visible, NASA might literally identify the origin points of the sunward jets, the antitail, and the complex shell structures. For the first time, we could match the comet's bizarre behavior with the physical features responsible for it. We might see active outgassing frozen in the frame jets erupting, dust lifting off the surface, plumes fanning out into space. That alone would confirm or refute several competing theories about what powers this comet's extraordinary activity. And then there's the question of size. Right now, estimates range from under 1 kilometer to more than 10 kilometers. HiRISE's images should end that debate instantly. A precise diameter means a precise mass. And a precise mass tells us whether the comet's enormous jets were physically possible or whether something else was driving them. Color information might reveal compositional zones, bright patches, dark scars, fresh exposures, radiation processed crust, or areas that look chemically different from one another. That would directly address the puzzle of why 3i Atlas glows green without the expected C2 molecules. And NASA might not stop at pictures. They've had 40 days to analyze the data, so today could include nucleus shape modeling, rotation state updates, outgassing simulations, revised size and mass estimates, coma structure mapping, comparisons with other interstellar objects. They may also present supporting data from other state debris, instruments aboard MRO like XRISM, the spectrometer capable of detecting specific minerals and ices. If XRISM managed to gather usable data, we might get the first direct chemical fingerprint ever taken from an interstellar comet's surface. There's also a more dramatic possibility. 3i Atlas passed perihelion just before the images were taken. If the nucleus showed signs of stress cracks widening, surface plates separating, or partial fragmentation, NASA might reveal evidence that the comet was in the middle of structural failure, or that it should have failed but mysteriously didn't. Both outcomes are equally transformative. Whatever NASA shows, one thing is certain: today will shift the entire conversation. Because these images, if they are as sharp as HiRISE is theoretically capable of producing, will become the definitive record of an interstellar visitor. Every theory, every argument, every anomaly will now have to confront what the surface actually looks like, and that's why NASA is treating this as an event, not a routine release. They know this dataset won't just answer questions, it will open new ones, it will correct assumptions, it will expose truths we didn't know to ask about. Today, the curtain finally rises, and for the first time, we will truly see the face of 3i Atlas, the ancient traveler that has challenged everything we thought we knew about comets, about interstellar objects, and about what moves through the deep galactic dark. The wait is almost over, and whatever appears on that screen normal, unusual, or something we never imagined will redefine the story from this moment on. For all the anticipation surrounding today's reveal, it's just as important to understand what won't be shown, what NASA simply could not capture, what physics and geometry prevented, and what the Mars Reconnaissance Orbiter was never designed to do. Because today's release, no matter how extraordinary, will still be incomplete. 3i Atlas was within MRO's view for only a tiny window of time, just a few hours, when the geometry lined up perfectly on October 3rd. This wasn't a long-term observation campaign. This wasn't a Rosetta-style escort mission. It was a point, shoot, and hope you catch something historic moment. That means the data we get today won't show rotation across a full cycle. It won't show the nucleus changing over days. It won't show outbursts as they occur. Instead, we're getting snapshots, incredibly detailed snapshots, yes, but moments frozen in time, and frozen moments hide as much as they reveal. MRO could only see the hemisphere facing it at the time of imaging. Whatever exists on the far side, possible vent systems, fracture networks, or even the source of the sunward jets, remains invisible. If the active regions sit on the hidden hemisphere, today's reveal might leave those mysteries unanswered. Even on the visible side, there are limits. HiRISE is extraordinary, but not magic. At 18+ million miles, there is a minimum feature size it simply cannot resolve. Micro cracks, fine textured ice deposits, subtle color variations, or thin dust layers all fall below its detection threshold. These features shape comet behavior in fundamental ways, but MRO won't be able to show them. And then there's the reality of data processing. What you'll see today isn't raw space telemetry. HiRISE images must be calibrated, corrected, denoised, contrast balanced, and geometrically adjusted. Every one of those steps involves choices. Scientific choices, necessary choices, but choices all the same. NASA will present the best version of the images, but another processing pipeline might emphasize different details. A different noise filter might reveal different textures. A different contrast stretch might bring out features NASA's chosen pipeline softened or ignored. Again, nothing nefarious, just the reality of converting raw sensor data into human-readable images. Then comes spectroscopy, or rather, the lack of it. If XRISM observed 3I Atlas, the results may not be strong enough to map detailed chemistry. The comet was faint, distant, unpredictable. We may get broad hints, ice versus rock, maybe major minerals, but not the fine chemical signatures that solve mysteries like the green glow problem or the unusual carbon dioxide dominance. And today's event will be focused solely on MRO. That means we probably won't see whatever Tianwen-1 captured beyond the early November images. We likely won't get anything from MAVEN or ESA orbiters. International coordination takes time, and time is exactly what NASA hasn't had much of. 40 days is barely an eye blink in mission analysis terms. There's also the uncomfortable possibility that something simply went wrong. Maybe pointing wasn't perfect. Maybe exposure settings underperformed. Maybe cosmic ray hits degraded parts of the frame. NASA would never hype a failed dataset, but the images might still fall below the breathtaking resolution some expect. Even perfect images don't guarantee perfect interpretation. If 3I Atlas's surface displays unfamiliar patterns, textures, or geometries, unlike solar system comets, the scientific community will argue for months about their meaning. Are they natural fractures, thermal shock, features, radiation scars, or something more exotic? Today will give us data, not certainty. And finally, the big question: will NASA release everything today? Possibly not. They may show selected highlights, processed images, curated frames, expert-guided interpretations, while holding raw data for later public release. That's normal. That's standard. But it means independent researchers, who often spot things mission teams miss, won't get to dive into the full dataset immediately, and that delays answers. Because some of the biggest discoveries in planetary science, geological patterns on Pluto, activity on Enceladus, jets on Comet Hartley, were found not by mission teams during press events, but by external researchers poring over raw data later. So yes, today will change the conversation. It will move the field forward. It will give us the clearest, sharpest images of an interstellar comet nucleus ever captured by human instruments. But it won't give us the whole story. Some mysteries will stay locked behind the limits of geometry, resolution, and instrumentation. Some answers will remain out of reach until other observatories, JWST, ground-based spectrographs, maybe even future spacecraft, fill in the missing pieces. Today is a milestone, not the finish line. A step, not the conclusion. A keyhole glimpse into an ancient traveller we are still struggling to understand. 3I Atlas will reveal more today, but it will not reveal everything. The story of 3i Atlas stopped being just a scientific investigation a long time ago. It has quietly grown into something larger, something that reveals how space exploration really works now that we live in a world with multiple spacefaring nations, competing scientific cultures, and fast accelerating technology. When China released its Tianwen-1 images weeks ago while NASA held its own data under review, that moment wasn't only about astronomy. It was about presence. It was about saying, without ever saying it out loud, that China now plays in the big leagues of space science, that their spacecraft can observe the same interstellar visitor the Americans and Europeans are studying, and that they can release their findings on their own timeline, without waiting for NASA, without waiting for anyone. That single choice sits inside a much larger shift. For decades, the story was simple. NASA leads, everyone else follows. NASA makes the major discoveries, NASA sets the pace, NASA shapes the narrative. But that's not the world we live in anymore. China landed on the far side of the moon, something no nation had achieved. China built its own space station when excluded from the International Space Station. China's first Mars mission nailed everything: orbiter, lander, rover, in a single attempt. These aren't just engineering feats. They are signals sent across the global space community. China is no longer trying to catch up. It is competing. And 3i Atlas fits directly into that new competitive landscape. China didn't coordinate with NASA, didn't wait for global analysis. They observed the comet with Tianwen-1, processed the data, and released their images straight to the world. A quiet, controlled, confident move. Meanwhile, Europe through Mars Express and the ExoMars Trace Gas Orbiter played yet another role. ESA missions refined trajectory models, provided supporting observations, and filled in gaps from different vantage points. Europe operates differently from both NASA and China. Its entire scientific structure is built around multinational cooperation, shared instruments, shared data, shared missions. So, 3 different institutional cultures intersect around one interstellar visitor. NASA's careful, review-heavy approach, China's fast, independent, strategically timed releases, ESA's collaborative model. And because of this, studying 3i Atlas has become a live demonstration of how 21st century space exploration actually works: messy, fast, competitive, and occasionally beautifully cooperative. But there are tensions too. When China released its images first, Chinese scientists had an immediate advantage. They published analysis sooner, they entered the global conversation sooner, they shaped early interpretations. For weeks, if you wanted the best data from the Mars encounter, the only source was China. NASA's delay may have been purely scientific: 40 days spent calibrating, verifying, and processing. It may also have involved presentation strategy, ensuring that when the data finally appeared, it arrived with full context and expert interpretation. Or it may have been both: rigorous science and careful messaging aligned. Either way, today's NASA release isn't just about showing images. It's about reaffirming NASA's role in an increasingly multipolar space environment. A reminder that even with new competitors rising, NASA still holds unmatched capabilities when it chooses to reveal them. And the global context matters even more because of what happens next. When the Vera Rubin Observatory comes fully online, we won't detect one interstellar visitor every few years. We'll detect dozens, maybe hundreds. And when that happens, what then? Will nations coordinate observations? Will spacecraft be jointly tasked to track the same object? Or will China, NASA, ESA, India, Japan, and others all race to capture their own data, publish their own findings, and stake their own claims? Nobody knows. The rules aren't written yet. 3i Atlas is giving us a preview. The United States, China, and Europe all observed it separately. All processed their data separately. All will release their findings separately. That fragmentation brings both redundancy and rivalry. It improves coverage, but it also pits institutions against each other in the quiet competition for scientific priority and global prestige. Today's NASA reveal sits inside that story. The agency will showcase its high-rise imaging, its analysis, its interpretations, It will emphasize the science. It will focus on what 3i Atlas can teach us. But underneath the scientific narrative is another narrative entirely about leadership, competition, and how space science is evolving in a world where no single nation holds the stage alone. 3i Atlas does not care about geopolitics. It flies through our solar system following physics, not politics. It is indifferent to whether the images come from NASA, China, or Europe. But we care, and because we care, the way nations observe, release, analyze, and frame data becomes part of the story, part of how discoveries shape prestige, part of how institutions position themselves for the future. Today, one chapter of that international story reaches a turning point. NASA finally reveals what HiRISE saw, and immediately, the next chapter begins. The final hours before a major NASA reveal always carry a particular kind of chaos, tension. Scientists who've been buried in the data for weeks are polishing their explanations, rehearsing how to walk audiences through what the Mars Reconnaissance Orbiter captured. Public affairs teams are checking stream quality, coordinating media questions, making sure everything runs smoothly. Journalists are preparing their background material, reviewing everything known about 3i Atlas so far, and drafting questions they hope to ask once the images are shown. And beyond all of that, a global audience is waiting. Professional astronomers, amateur observers, and countless people who've followed every twist of this story are watching the clock. Everyone feels their own version of anticipation, some rooted in scientific curiosity, some in skepticism, some in hope that today finally brings clarity after weeks of speculation. Amateur astronomers who've tracked 3i Atlas night after night wonder whether the features they reported will appear in NASA's images. Researchers with competing interpretations of the comet's behavior are hoping the data tilts in their direction. The community arguing for conventional explanations wants to see a straightforward comet nucleus. Others who expect something unusual are watching for features that could signal deeper mysteries. Avi Loeb and anyone following the technological artifact angle certainly have their eyes on this moment as well. The images could reinforce natural explanations or open the door to more unconventional discussions. Media outlets are already preparing multiple headline variations, waiting to see which one fits the actual reveal. Social media communities are speculating about when, within the 3-hour broadcast window, the first image will appear. Will NASA begin with context, or will they open immediately with the highest resolution frame? Will scientists take questions? How much will be explained, and how much will be left for the scientific papers that follow? Chinese researchers are watching too. Their Tianwen-1 images have been the only Mars orbit visuals of 3i Atlas available for weeks. That changes today. How will MRO's imagery compare? Will it reveal details Tianwen-1 couldn't see? Will it confirm or contradict any features noted in the Chinese release? European scientists are waiting to see whether their contributions, especially the orbit refinement from the Trace Gas Orbiter, receive acknowledgement during the presentation. The story of 3i Atlas has been shared across multiple agencies, and today's reveal will crystallize how those contributions fit together. But underlying all of that anticipation is one question no one says out loud, though nearly everyone feels. Will today's images actually solve the mystery, or will they deepen it? If the nucleus looks like a typical comet, irregular, dusty, and what you'd expect from billions of years of space weathering, many of the so-called anomalies could settle into natural explanations. The strange jets, the sudden brightening, even the rotation patterns might end up fitting within known comet behavior. But if the nucleus looks unusual, odd shapes, unexpected surface patterns, structures inconsistent with normal radiation process crust, then the mystery only grows. That kind of data wouldn't close the discussion. It would ignite a new one. And there's always the third outcome, images that are impressive but not definitive. Details clear enough to tease possibilities, yet ambiguous enough that interpretations diverge. That is often how real science works. Answers arrive in pieces, not in perfect cinematic revelations. Still, the emotional momentum leading up to today has created a global expectation. After 40 days of waiting, people want closure. They want clarity. They want something that either reinforces the familiar or opens the door cleanly to the extraordinary. But the reality will likely be a mix, some clarity, some new, puzzles, and a few surprises no one predicted. What is certain is that these images will become the benchmark for 3i Atlas. Every future discussion, every model, every scientific debate will trace back to what is shown today. These will be the highest resolution views of an interstellar object ever captured. Somewhere inside NASA's servers, the files are ready, the processed frames are queued, the commentary scripted, the technical checks completed. Around the world, people are setting reminders for 3 p.m. Eastern, marking the moment when the 40-day wait finally ends. Some will watch the stream live, others will analyze the released frames in detail. Researchers will be examining pixel-level features by tonight, and the images will spread through every corner of the internet within minutes of unveiling. This isn't just another comet flyby, it's our closest look at material formed around another star system, shaped by conditions unlike those in our own. An object that has travelled through the galaxy for billions of years, carrying chemistry from environments humanity has never directly witnessed. Today, for the first time, we see it clearly. Understanding moves forward, new questions rise, the long speculation ends, and the next chapter begins. The countdown is over. The reveal is here. Why did it take 40 days? That single question has hovered over this entire story. It shaped speculation, amplified curiosity, and opened the door to interpretations ranging from calm patience to full-blown suspicion. Today, we'll likely get the official explanation. Maybe it really was technical calibration. Maybe it was the need for careful scientific review across multiple teams. Maybe it was simply the time required to turn raw spacecraft telemetry into high-fidelity images. All of that is reasonable. All of it makes sense. But even if the explanation is completely ordinary, the question doesn't disappear, because this isn't just a matter of scheduling, it's a matter of how information moves, who controls it, and how the timing of knowledge shapes public imagination. In a perfect world of pure scientific openness, telescope data would appear instantly. Raw frames would flow into public databases within hours, ready for anyone to analyze in real time. But the real world works differently. Institutions rely on checks, calibrations, reviews, protocols, communication plans, the machinery of responsible science. And yet, in the silence between observation and release, the world began writing its own story. For some, the 40-day delay felt routine. For others, it felt deliberate. And what people projected onto that silence revealed more about us, about human psychology, than about the comet itself. Because 3i Atlas represents something far larger than a delay. Is it just an unusual comet? Is it a preserved shard of early galactic chemistry older than our sun? Older than Earth itself? Or could it be something that simply doesn't fit the categories we've been using? The images arriving today may clarify the picture, but they won't close the book. They show the surface, not the story. They reveal shape, not origin. They solve one layer while exposing another. We've only ever seen 3 interstellar visitors in human history, 3 data points out of trillions wandering the galaxy. Oumuamua showed us strangeness, Borisov showed us familiarity. 3i Atlas shows us complexity and challenges every assumption we built from the first 2. And it reminds us of something profound. The galaxy has had 13 billion years to experiment. It has forged planets around metal-poor stars, massive stars, stars that no longer even exist. Every one of those systems has been ejecting material for billions of years. 3i Atlas is one shard of that endless dispersion, a time capsule carrying chemistry from cosmic eras long before Earth formed. Today, we finally see its face. But seeing a messenger's face is not the same as understanding its message. Why did China release its images immediately? Different philosophy, different rhythm, different culture. Why did amateurs detect unusual behaviors before official channels spoke up? Because curiosity moves faster than bureaucracy. Because backyard telescopes now produce professional-grade data. Because the line between amateur and professional astronomy has dissolved. Why does 3i Atlas behave the way it does? Maybe it formed in a planetary system with different chemistry. Maybe billions of years of radiation reshaped it. Maybe our models built entirely on solar system comets simply aren't broad enough. Or maybe There's something here we haven't understood yet. The images arriving today will help. They'll refine hypotheses, close some doors, and open many more. But they won't end the mystery. They'll deepen it in the best possible way, because real science doesn't eliminate uncertainty, it transforms it. It turns "we don't know anything" into "now we know exactly what we still don't know." That's progress the kind 3i Atlas has forced upon astronomy again and again. Its sunward jets, its anti-tail, its COTWO-dominated composition, its survival at perihelion, its strange, layered coma. Each observation widened the puzzle rather than solving it. Today's images will do the same. They'll expose features nobody predicted, they'll demand new models, they'll challenge assumptions, they'll push us into theoretical territory we've never had to explore. And above all, they remind us of the era we're living in. For the first time in history, humanity can track objects from other star systems entering our solar neighborhood. We can position spacecraft around Mars, another planet, to photograph them up close. We can share those images instantly with billions of people. 3i Atlas is a gift from the galaxy, a relic from before Earth existed, a traveller shaped by physics older than the Sunday. It wandered for billions of years across distances beyond imagination, and for a brief moment it passed close enough for us to study. Today, the images arrive. Images humanity has waited 40 days to see. Images that will echo through research for decades. Images future generations will revisit when interstellar missions become routine. Why 40 days? We'll hear the explanation soon, maybe ordinary, maybe complicated, but that question shaped the narrative because it revealed how discovery, secrecy, curiosity, science, and imagination collide in the modern world. Today, the boundary shifts again. Another piece of the cosmic puzzle clicks into place. Another ancient traveller reveals part of its secret. Another chapter in humanity's encounter with the galaxy opens. The countdown is nearly over. The images are about to become public. 3i Atlas is finally ready to be seen with clarity, and once we see it, the real questions begin. As we stand on the edge of reveal day, one truth settles in. We're witnessing the beginning of a new chapter in our understanding of the cosmos, driven not by certainty, but by curiosity, patience, and the willingness to follow evidence wherever it leads. In just a few hours, the first high-resolution images of 3i Atlas will enter the public domain. Not rumours, not speculation, real data captured by one of humanity's sharpest eyes, released for the world to see. What happens next belongs to the global scientific community. Researchers will analyze every pixel. Amateurs will compare with weeks of sky monitoring. Students, journalists, and enthusiasts will join the conversation. Some theories will strengthen, others will dissolve. New ideas will spark, and slowly, piece by piece, the story of this ancient traveller will come into focus. Whatever today's images reveal, they mark a moment in history. A moment we'll look back on as the turning point in our exploration of interstellar visitors. A moment when we looked beyond our solar system, not just with imagination but with clarity. So as the countdown reaches its final seconds, remember, we're watching science happen in real time. We're watching humanity learn. We're watching a piece of the galaxy's deep past drift through our present, leaving knowledge in its wake. With that, we close this chapter for now. More awaits on the other side of the reveal. As always, clear skies, everyone.